All right, so welcome to Santa's Lair, the not-so-random PRNG section. And essentially now what we're going to do is fight Santa. And Santa's going to have a series of moves that he's going to throw at us, and it's going to be completely random. Or so you might be led to believe. It turns out that when generating random numbers, generating good random numbers is actually really hard. There's a really awesome video on YouTube, I'll post a link to it, how Cloudflare does randomization for some of feeding a lot of its algorithms. So essentially what it ends up doing is having a wall of lava lamps that are constantly in motion and moving, and there's a video feed on them. And it ends up taking a lot of those characteristics and differences between frames and using those to seed these generators or algorithms. That type of chaos, or the amount of data that's constantly flowing and changing based on the temperature and ambient light and all these different characteristics, is really important to the chaos and randomness. If you try to develop an application that generates a random number, typically that particular generation, no matter how random it might seem, is probably not super efficient or as efficient as you think. It turns out that a lot of the types of ways that you can generate random numbers are absolutely not recommended for cryptographic use. It turns out that there are specific operating systems will have specific forms of sort of cryptographically approved or cryptographically acceptable, I guess we'll say, forms of entropy. And those particular methods should be used versus something that you roll yourself. It turns out to be a really important part of just generating random numbers and seeding specific processes. So what we're going to see is a failure in that particular case, or to understand that situation. So when we go to fight Santa, we have to actually do this in a specific way. So remember before that when we open the application, the prompts that we had were 1 through 4, and we didn't get anything else. So we have is this unknown area. So now that we have more keys, let's go ahead and try entering that unknown option, 25. Now all of a sudden we get something. All right, here we go. This is Santa's lair. It says you enter Santa's lair. The hair on the back of your neck begins to stand on end. Ho, 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 no you don't. If you want my list, you'll have to get through me first. Santa rips a shiny key from around his neck and swallows it. Santa charges. Okay, here we go. We have a action list. 0, 1, 2, or 3 are the actions that we can use. That's to dodge and counter a right punch, a left punch, a right kick, or a left kick. Santa is so fast that we need to pick an action before he does. So he has super high resolve and dexterity. What we're going to do is try to beat Santa at his own game. Let's go ahead and type in 2 just as a random guess. Oh, he comes at you with a right kick. This is attack 1. Hey, look at this. We counter Santa's combat move and connect with our own. Let's keep going. What do we do? Why don't we do a 3? Santa throws a left punch. Santa connects and knocks you through the wall back into the main lobby. Okay. So this is not good. We have to try to beat Santa at his own game. So let's see if we can end up doing that. Let's take a look at the code and get an understanding of what's going on here. Now that I know that this is Santa's lair, I can change my unknown generic name to Santa's lair. Perfect. So let's go ahead and go in there. And what we're going to end up seeing is some type of memory buffer that's being set to 0. That's like a memset. There's some system call to CLS. It's clearing the screen. And then we come down to this location. It asks us for an action. And then it says we either do something, attack, or not. So this is great. So it says action. It'll read it. It scans it, passes the information into this function, and then either returns 1 or 0. So there are some shifts and other things here. Essentially what this ends up doing is determining whether or not we hit Santa. So what we want to do is try to understand what the conditions are for actually triggering this stuff. Now if we go up a little bit more, we end up seeing here is this SRAND. And typically what happens is if you ask for a random number, you'll get the same pattern over and over and over again unless you seed rand. And then you'll get some random number based on that seed. Now it turns out if you use the same seed, then every single time you run, you'll get the same exact value. So let's take a look at this as an unsigned decimal. It looks like 1225 is being passed into srand, and then after that point, we end up doing a specific sequence that ends up calling rand and then putting out some particular value. And let's see, we don't know what that is. That is going to be a resolution to the action that Santa does, and then it'll return whether or not we connected or not. So this is, let's see here, not Santa's move, but we'll just call it like it does connect or something like that. So this is, do we actually like hit Santa? Does Santa hit us? All right, so in this particular case, this does connect. We'll either go down to Santa connects, or you can't counter Santa's move. So this is important for us. We have an unknown number of times that Santa will actually ask us. As a matter of fact, we actually know this because this right here is a loop. We talked about this before in an earlier video, and we end up comparing this guy who gets incremented by 1 every single time we come around here, and it gets compared against 17 hex. Now 17 hex is 23, so it turns out that this happens jump if less than or equal to this location. If it's jump if less than or equal to, that means that we're being asked at 23 times because of 0, I believe, or 24 times. So we'll end up having like a 0 index into this guy, which is the first time it comes through will be 0, and then it'll increment. So essentially this will end up happening 24 times, and then it'll end up going down this particular path here. And the whole goal of this is that we don't actually get connected with and then end up failing or being kicked out of the room into the main lobby. What we want to do is set this byte, which is the keychain, to collect the last key, and then fire off this guy, which says we approach the vault. This is good. We want to get down to this particular location. So in order to do that, we need to know this byte pattern. Now what I've done is compile the version of what's actually happening in here. So we have this small C application that seeds random with 1225, which is what Santa seeds it with. And then we just do 50 times. Since we actually know that there's a specific number here, we can go ahead and recompile this. And what we're going to do is print out the index that we're doing plus 1, so it's not 0 indexed, it'll just be at 1. And then we can print out the value that gets generated by random. So we use this modulo 4 to represent, basically mask off any values that are larger than that. We essentially are generating anything between 0 and 3 by doing this modulo 4. Okay, so what we're going to end up doing is just compiling that real fast. So let's do this. All right, and then let's go ahead and run it. Okay, so here's what it gives me. It gives me the first move should be 2, and then 1, and then 0, and then 0, and then 0, then 1, and 0. Okay, so this is what I think it is. Now it turns out that all random number generators are a little bit different. This is MinGW on Windows, and if I come back here and do that same exact code here, which I've already compiled, and end up running it again, I'll press up forever to save 4 keystrokes. It turns out that the pattern is way different. So even though we seed srandom with a same value, the 1225, as we do over here, as we saw in this location, it turns out that we end up getting a 3, a 2, a 2, a 3, and if we come back to this output and take a look here, we don't actually get a 3 in any of these, which is really interesting. It means it takes at least 23 times or 24 times in order to get a 3. That doesn't seem very random. But the process, or the thing that it's important to remember here, is that there's different implementations of this random number generator. This is MinGW, which implements the GNU compiler toolchain in Windows. So it's GCC over on this guy. And this guy is like Clang LLVM on this side. So there's actually different implementations of the random number generator that are being used. If we go to Python and ask it and seed it and do it that way, we'll get completely different values also, even though we end up seeding it with something. So the process of doing this is typically getting a timestamp, like the current time, down to a really high precision or value, like to the microsecond or something, and then putting that particular value as a seed into SRAND, and then starting to generate numbers. If I were to take the date as a year and pass it into SRAND and then start generating numbers, that will be valid for the entire year. So if we did the month, it'll be valid for a month, and then the time as an hour or a minute or a second will be that particular resolution that we can actually regenerate those numbers and know what actually happens. So it turns out that we want super high precision and all the little nuances that things have changed all the time. So when I talked about that Cloudflare example, where they're taking all the chaos and randomness from movements and slight subtle differences inside of those bubbles inside of the lava lamps, they end up just hacking off all of the most significant values and taking those smaller kind of most chaotic pieces and feeding that into the random generation. So in this particular case, what we can do is, since I know that the application was generated with this particular compiler, I can recompile this chain and it should end up working. If I don't know what compiler was used, essentially we need to go through this process and brute force it. We would have to say, all right, well, we got kicked out, one didn't work. Let's go into 25, and then say, okay, one didn't work. And then we'll go into 25 again, and then we'll eventually get to 2 and it will work. And then we'll set at 0, and then it'll kick us back out. And we have to continue doing this process to understand how that works. We could also try to understand this piece right here, but keep in mind that we're getting the value back from random, which is implemented in this Microsoft Visual Common Runtime, which is not something that we want to bring up and start reverse engineering. It's almost easier to just do this pattern and try to do this. We can actually script this interface and try to brute force it that way. But since I know the actual compiler that was used for this, I can sort of cheat and just generate all the numbers ahead of time. It turns out we can also patch this application to always return success and then print out the value that was actually being compared against. So what we can end up doing is just doing a little binary manipulation and have the application actually print out this pattern for us so that we can come back into a non-modified version and type this all out. So let's see if recompiling this actually ended up working. Hopefully it does, otherwise that'll be bad. 2, 1, 0, 0, 0, 1, 2, 2, 0, 1. All right, attack 10. That worked. I don't want to get off guard here. 0, 2, 1, 2, 0, 2, 2, 0, 0, 1, 2, 0. This should be the last one too. No, there's one more action. All right, so it was wrong on this. Let's go here and do 24. Let's just do 30. All right, come on. Let's see. Oh no, that's not good. Jeez, come on. All right, let's see here. What are we on? So we just did 23. Now we're on 24. It's a 0. There we go. We're off by 1. Easy to do. All right. So we beat up Santa and we go to the vault. We turn keys 1 through 4. Our eyes scan to the 5th and final keyhole. We turn towards Santa as the horror of what needs to be done sets in. Minutes later, Santa's vault whooshes open, revealing his list. Enter your name. All right. You step back and smile as you read John at the top of Santa's list. All right. Santa's hand rests upon your shoulder. Ho, ho, ho. Gagging me with a candy cane as a way to get the key. Good one. You and Santa, high five. The end. All right. So obviously this is kind of like a silly example of an application that we have to reverse engineer, but there are interesting challenges that sort of talk about or try to illustrate some of the things that you'll end up seeing in real applications as you start reverse engineering. And hopefully this process of pulling back and looking for specific patterns, this idea of gestalt, and being able to like re-implement the types of things that you end up seeing in applications that you're reverse engineering, and building small tools to try to help you get progress, and all of this are all pieces of what reverse engineers do. It's a process of debugging applications. It's a process of trying to understand how they work. And although we looked specifically at how we do this as software reverse engineers, this same type of process, again, is applicable to so many different industries and fields. So I hope you learned something new. If not, I hope you enjoyed watching me get really tired as it's 2 o'clock in the morning and stumble over things like an off by one issue. But other than that, that's pretty much it. Let me know if you have any questions. If not, thanks for watching. See you later.